All right, so let's look at a couple more examples where we get to practice working with functions. So in this example, what we're asked to do, there's two functions, right? In part A, we have this function. In part B, we have this function, which is the one we just dealt with. But in both cases, we're going to find this is called the difference quotient, by the way. You don't need to worry about the terminology. This is actually something that turns out to be very important in calculus. If anyone goes to study calculus, you'll encounter this fraction many times. But that's not super important for us right now. We're just going to use it as an opportunity to practice. Okay, so what's this going to look like? Well, let's start with part A. So, the first step is going to look a lot like just writing out this expression. So I'm going to start far to the left just so we have enough room to fit this in. So f of x plus h minus f of x, and then all of that is divided by h, right? Okay, so that's the first step is just identifying what we're working out. So now on our next line, we're going to actually take this f of x plus h and replace it with what its definition is. In other words, we're going to plug x plus h, which is our input value, we're going to plug it in for the x here. And then we're going to get a corresponding output value over here. So we're going to have 2 times x plus h minus 5. I'm going to put square brackets around this just to emphasize that that's all one piece that came from f of x plus h, right? Because that's what we would get. If you plug in x plus h for f, you're going to end up with an x plus h here. So you'll have 2 times x plus h, all minus 5, which is what we ended up with here. But that's not everything, right? We still have the minus f of x to worry about. So we have minus, well, f of x is just 2x minus 5. So let's replace the f of x with its definition. So that is our numerator. And then all of that is divided by h. Okay? So that's our second step. Okay. And now, well, there's two things that we should probably do. First would be to distribute the 2 into the brackets. And then the second step, we can take this negative and distribute it into the brackets. Okay, and what this is doing is this is called expanding everything out. We're reducing the number of brackets that we need. So we'll have 2x plus 2h minus 5, right? And all of this, I don't actually need these brackets, but all of that is really just coming from this chunk here. Okay, so since those brackets don't actually do anything, I'm not going to include them because then we'll just need to take another step to get rid of them. But now for the rest of it, I'll have minus 2x and then plus 5, right? Because this was a negative 5, but when that negative hits it, it'll be a positive 5. And then all of that is still divided by h. Okay, well now let's look at what's going to cancel. This is why you often want to expand things out, because then you'll start to see things cancel, right? For starters, the negative 5 and the positive 5 will cancel nicely. Oh, and hey, we've got 2x and negative 2x. Those will cancel out as well. So what we're left with is finally just 2h. So we have 2h, and hey, the denominator was h, so we can even do another cancellation since h is a common factor of the numerator and the denominator. So we end up with just 2. Okay, so 2 is actually what this all boiled down to. This all simplified down to just simply 2, right? Who would have thought something that complicated would just boil down to just the number 2? So that's quite nice. Let me add another cautionary note here. If this had have been 2 plus h over h, this is a common error that people make. People try to say, okay, well, there's an h up top and an h on the bottom. I'll cancel them both, and then I'll just be left with a 2. But that does not work. So again, what I've written here is not correct. So I'm going to put a line through it. Okay, you cannot cancel the h from the top and oops, didn't mean to do that. You can't cancel these h's. Why? Because they're not common factors, right? This is addition. 2 and h are being added together, not multiplied. So for that reason, you cannot cancel the h in that case. So watch out for that. That's a really important thing to watch out for. I'll just put a box around this so it's separated from the rest of our work. Okay, so what about in case number 2, where we've got this one, f of x is x squared plus 1. Well, let's start from the beginning. We're going to go f of x plus h minus f of x. all divided by h. So that part is just because that's what we're asked to work out, right? So nothing mysterious going on there. But now we're going to actually replace this occurrence of f of x plus h and this occurrence of f of x. We're going to replace them with their definitions, with their corresponding output values. So we're going to get x plus h squared plus 1. That's the f of x plus h. Then we're going to subtract f of x, which is, well, just x squared plus 1. Okay, and that's all divided by h. Okay, so now what are we going to do? Well, in the next step, what I'm going to do is I'm going to take the x plus h squared and I'm going to expand that. And then over here, I'm going to take this negative and distribute it into the brackets. Okay, so what am I going to get? Well, and you know what? It wouldn't hurt to just work this out carefully. So x plus h squared, we've got the space, so we'll go x plus h times x plus h. So what are you going to get? You're going to get x squared plus hx. Well, and let me draw the arrows to be clear what I'm doing. So that's x squared. Then I'll have x times h. And here I'll have h times x, which is just the same as x times h. And then finally, h squared. So we're going to get x squared. And I can combine these two together to get 2xh plus h squared. But it's very common to do that all in one step because this is a standard this is a standard expansion formula for this is called the square of a binomial expression. So there's two terms. The x and the h are two separate terms, and then we're squaring it. There's two separate terms added together, and then we're squaring it. It always fits this form. So quite often, you'll see people just do that in one step without showing the details. Okay, but if you ever aren't sure what to do, this is the way to check. Just do it carefully, term by term. You can never go wrong doing that. Okay, so let's go back to what we're doing. So we have x squared plus 2xh plus h squared. So that was all of this. Then we still have plus 1. And then we'll have minus x squared minus 1. And then all of that is still divided by h. Okay, so let's look at what's going to cancel. Well, we've got an x squared and a negative x squared, and we've got a 1 and a negative 1. So that's looking pretty good. All we're going to have left is 2xh plus h squared all over h. Okay, and we can actually do a little bit more here because notice that the two terms in the numerator, they both have a common factor of h. Let's actually factor it out. So I'm going to go, I ran out of room, so I'm going to go back over here now to continue. But so let's factor out an h. We're going to have h times 2x plus h. That's what will be left if I factor out an h. Then I'll have an h on the denominator. So why did I want to factor that out? So that I could cancel it with the h on the denominator. Okay, and then we're going to be left with 2x plus h, and then that's as far as you can go. Okay. So that's, again, that's called a difference quotient. You encounter it quite a bit in calculus, but in our case, we're just using it as an excuse to practice working with functions and simplifying them. Okay, so the next comment you see here that says sometimes functions are defined using different rules for different sets of input values. This is a special type of function, which is called a piecewise function. So let's add a comment. These functions, the ones that are defined in this way, are called piecewise functions. And they're still functions just as much as any other function. They're just sometimes they just take a little bit more time to write down and express. Okay, so let's look at an example. And this is actually a function that you're very familiar with, but you may not be familiar with seeing it in this fashion. So what do you see here? Well, it starts off just like any other function would, right? We have the name of the function is f, and then it says f of x. So you can tell that x is going to be used as the input parameter. But then after the equal sign, you see this bracket. Okay, and that's where things now we're going. It's different than what you're used to seeing. But how do you interpret it? Well, it just means that you're going to define your output value based on different rules for different cases. So here are the cases. These are both possible cases that could apply to the input value. Either the input value could be greater than or equal to 0, or it could be less than 0. So the idea is this. The way you read this out loud, and let me do another arrow here so we can kind of go through the process of reading this. So we got our function f. It takes an input value x, and then it does one of two things. If x is greater than or equal to 0, it just gives you back x. But if x is less than 0, then it gives you back negative x. Okay, well, let's play around with this a bit. Let's see. Let's try to actually put this in action. So how about this case? Part A says to work out f of 1. Okay, so you're going to take the value of 1, and then you're going to jump to these cases, and you're going to say which of these two inequalities is true when x is equal to 1. And, well, it's the top one, right? Because if you plug in 1, you're going to get 1 is greater than or equal to 1. That's true. But if you plug in 1 here, you're going to get 1 is less than 0, and that's not true, right? 1 is not less than 0. 0 is less than 1. It's the other way around. So because of the fact that this is a true statement, that means we're going to use this as the rule to determine the output value. So, but remember, x is the symbol that represented the input value, right? So if it's you might as well just take it to be f of x is equal to x here. So we're just going to get 1 back for the output. Okay, and I'm going to just add a reason here. The reason for this is that 1 is greater than or equal to 0. So because this statement is true, we used this rule and we just gave back the input value. Whatever the input value was, we gave it back as the output value. In this case, it was 1. Okay, what about 3? Let's plug in 3. Okay, so imagine 3 takes the place of x. So you jump over here and say, okay, which one of these two statements is true? And again, it's the top one, right? 3 is greater than or equal to 0. It's not smaller than 0. It's greater than or equal to 0. So, okay, well, that means this is going to be the rule that we use to define the output value. So if the input value was 3, the output value is going to be 3 as well. So we just get 3, and the reason is since 3 is greater than or equal to 0. Okay, so if you're finding this weird, hopefully the next example is really where it clicks, because now what we're going to see is the opposite case holds. So now let's plug in negative 5. So, okay, well, if you take negative 5 and plug it in for x, which of these two statements is true when x is equal to negative 5? And the answer is, it's this one, right? Because negative 5 is less than 0. So what that means is you're going to plug x equals negative 5 into this expression instead. So we're going to have negative, because of that negative on in front, but then x itself is equal to negative 5. So we have negative 5. Okay, so what does that give us? It gave us positive 5. Okay, and the reason for this, in other words, the reason we used this rule is because negative 5 is less than 0. Okay, so let's try a few more. So f of 0, let's try f of 0. So f of 0, oops, wrong color. By the way, why am I so picky about colors? Why am I doing these in green? Because you wouldn't normally write those down. If you're working out a function like this, you would just work out the value. You don't have to explain why you're using the particular rule. These are just annotations between you and I to help clarify what I'm doing so that you can understand it better. But it's quite standard to just not include those. But for our notes, we'll include them. So that's why I'm writing them in a different color. Okay, f of 0. Okay, well, plug in 0 for x. And then say, okay, which one of these statements is true? And the answer is this one, right? Because 0 is greater than or equal to 0. 0 is greater than or equal to 0 is a true statement because they are equal, in fact. But if I write 0 is less than 0, that's not true because 0 is not less than 0. 0 is equal to 0. And the strict inequality that you see here does not allow, or pardon, yeah, that strict inequality symbol does not allow for equality. But this symbol does allow for equality, and that's why that's the true statement. So you're going to go over here and plug 0 in for x in that expression, and you're just going to get 0, right? So f of 0 is just going to be 0, and again, the reason we use the first rule is because 0 is greater than or equal to 0. Okay, two more. F of negative 6. Well, same thing as we did before, right? Plug in negative 6, the same as the negative 5, really. Plug in negative 6, and you're going to find that this is the statement that's true now, when x is equal to negative 6. And for that reason, you're going to plug negative 6 in for x. But this extra negative sign in front is going to be important. So we're going to have negative 6, and that gives us a double negative, which is going to give us positive 6. And again, that's because negative 6 is less than 0. Okay, so for our final one, we've got we've got f of negative pi. So how are we going to do this with negative pi? Pi is a weird number, right, that we don't know exactly. So negative pi seems like it would be probably even worse. But it's actually not so bad, because what do you know? If x is negative pi, we don't know, well, I mean, we do know what pi is theoretically, but we don't know how to write it down in terms of all its decimal places because they go on forever without a repeating pattern. But we still know symbolically what pi is, and we do know that pi is a positive number, right? Because remember, if I sketch the number line really quickly, if let's say that's 1, 2, and 3, pi would be over here somewhere, right? Because pi is approximately 3.14. So, but that's even more detail than we need. The point is pi is positive. So if we put a negative sign in front of it, guess what? It's negative. So negative pi is a negative number. So that means this is the statement that's going to be true when x is equal to negative pi. So for that reason, we'll plug negative pi in for the x, and then we're going to get negative pi, and then the negatives cancel, just like they did in the last case, and we'll just end up with pi. So this is since negative pi is less than 0. Okay, I'm going to erase these because I want to add something else after. I need some space to do it, and that's not going to make sense later anyway. And I'll just put a box around this to separate it from everything else. Now, okay, notice that in all the cases where we had negatives, we highlight them. In all these cases, what happened? The input value was negative. So then what ended up happening is we ended up plugging the negative input value into this expression, which in effect, this gave us an extra negative sign. So if you take a negative value and then put another negative sign in front of it, what happens? It ends up becoming positive, right? That's what happened in all three of those cases. Okay, so we plug in negative 5, we got positive 5. Plug in negative 6, we got positive 6. Plug in negative pi, we got positive pi. What happened when we plugged in the positive numbers? Plugged in 1 over here, plugged in 3 over here, and well, 0 is not positive, but at least it's non-negative, right? It's greater than or equal to 0. It's something that's not negative. So what happened when we plugged those values in? Well, we just got the same value back. So plug in 1, you get 1. Plug in 3, you get 3. Plug in 0, we get 0. But if you plug in a negative number, the negative sign was just dropped. There's a name for that function. It's called the absolute value function, but you may not be used to seeing it as a piecewise function. Usually, it's introduced in a geometric fashion in terms of describing how it works in terms of measuring an input value's distance from 0. But let's add this as a comment because this is worth acknowledging. This is called the absolute value function. Okay, so in other words, we could have written f of x is equal to the absolute value of x. So this is another way to define the absolute value without having to refer to terms like distance and distance from zero and whatnot. This is a strictly algebraic definition of the absolute value function. But the important part here is just to show you how to work with piecewise functions, because we will encounter those again. Okay, two last comments for this page. This is just terminology. So remember what we said, when you have a function, you plug values in and you get output values that correspond to those input values. The idea here is that if you take all of the possible input values for a function and you put them together and call it a set, put them together into a set of objects, then you get what's called the domain of the function. So the domain of a function is just a set of all possible input values that you can plug into it. And then if you go the other way and say, well, what about all the possible output values and put them together into a set? Well, that's called the range. Okay, so those two terms are important. They're important aspects of any function, and we will take a look at them next.